Start. All right. So this is Team 49's preliminary design review with the L Space Academy Level 1. Here today we are presenting Mars Hydro with Clifford Alvarez and Colson Aguirre. The rest of the team members uh, helped out a great deal with this project, and unfortunately they could not make it due to school reasons. So me and Clifford are here to help out the rest of the team. So Clifford, say hi.
Hello.
So I don't know if you could see him on the camera, but you could definitely see our PDR. So that's all that matters. So we'll go into the preliminary design review. Just the criteria that L Space Academy has provided us for what they want out of us our and our metrics. If you hear any cars in the background, that's probably just my street being all crazy. So here's our members of Team 49. We got me, Colson Aguirre. We have Clifford Alvarez. We have Midu, Aaron Howard, Christina Keith, Jisun Kim, Jesse Corson, Hannah Smith, and Arturo Zaragoza. To begin, we'll start off with the descent summary. Similar to most large-scale missions to Mars, it is crucial to house our payload in a re-entry vehicle. Like many of the methods used to land the Curiosity rover and the InSight lander, we will be using the same methods to land our payload. Within this descent summary, we have 4 phases: an entry phase, hypersonic phase, parachute phase, and terminal descent phase. Here we have like a nice little diagram to show how we want to get our payload down just by using, I believe it's the Opportunity rover as a diagram. Here we'll go into entry and descent and landing with a little more detail. And down here we have our reentry vehicle that we've designed on CAD and exploded in assembly. And here's some dimensions of our reentry vehicle CAD model. And then now we're going to go into the payload summary. So our payload will be sent to the Morex crater, and our payload will weigh about 3.7 kilograms, and the volume should be about 8,412 cubic centimeters. The payload will be outfitted with scientific instruments that will allow us to complete our mission. Within these payload instruments, we will have a drill/temperature probe. This instrument will be used to drill down into the soil slash drill into the Martian soil and acquire the temperature of the ice that we are drilling at. Next, we would go into our communications package, which will be allotted with transmitters to communicate to various satellites to send our data back and to let Earth know that we found water or ice in our region. Next, we would talk about our spectrometer. Our spectrometer will be used to determine what kind of ice our payload's going to be looking in, and what kind of ice will it be? Will it be CO2 or H2O? Next, we'll be talking about the ground penetrating radar. The ground penetrating radar works a little bit different than the drill. Instead of actually drilling down and just seeing if there is ice down there, we'll have radar to identify in the ground if there's any anomalies underground before we start drilling, so we can identify those rocks or any of that ice underground and see how deep it is, and if our drill can reach those depths. Next, we'll have meteorological equipment. This will just help with future NASA missions understanding the climate and the environment which our payload is in for future human space exploration missions, if we do find water present in the crater. Just some more defined mission elements. So our spectrometer we're using is an alpha particle X-ray spectrometer. We're going to be using something similar to the rover environmental monitoring station, our REAMS. We have our drill and thermal probe, and we have our ground penetrating radar for our instruments. And then Clifford's going to take it away with the evolution of the project.
So changes made to the descent and lander criteria. So some changes that were made, that were done to the lander criteria were when we decided on our reentry vehicle to Mars atmosphere. We first planned out as like a sky crane when it hit a certain altitude, and when a specific altitude, it would use thrusters to slow the descent. So then we then change this idea to a typical parachute to slow down our vehicle. This allows for less complexity and less weight that is added on the payload. And for the changes made to the payload criteria, through brainstorming, the whole team agreed to make the payload be multiple drill projectiles that would detach from the descent vehicle and penetrate the ground at a specific speed allowed by a parachute. It would then start to drill and conduct multiple tests from a greater radius. This was later changed to a more simpler concept due to weight and size constraints. There would now be one payload with multiple legs that we will have drills embedded inside. When the payload lands softly on the surface, the drills will activate and drill into the surface. And some changes made to the mission experiment implementation plan. So acquiring a sample of soil for analyzing, radar to identify the depth of the ice underground, and using one drill due to weight constraints and the ability to add computer equipment and stronger materials for high drills mission. And finally, the addition of component to identify surround environment hydro will endure for future NASA missions. And for the payload science objectives, so our science payload consists of drills and spectrometers on each probe, a transmitter which is part of the communication package, and meteorological experiment on one of the probes. Each instrument of our science payload has a specific purpose that each contribute to completing the mission's objective. And these scientific instruments combined with our 7 probe system will allow us to categorize the water stock in the multiple areas of the crater, collect data to confirm or deny the presence of water in the crater. So below we have the we have it labeled for optimal, nominal, and mandatory for the mission objective. And here we just have some images of the landing sites and the site factors. So like potential for past habitability and potential for organic matter with surface exposure, high likelihood of active traces of gas sources, and near surface ice, glacial, and permafrost. So just a description of the crater that we will be landing on is located in the north part of the Terra Sabia. The crater has a region of sand dunes on the crater floor, as well as features that are similar to glacial topography on Earth, and the glacial flows occur from both the crater rim and the central crater peak. And glacial activities creates fine scale materials, which means the source of the dune sands may be local rather than material blown in from outside the crater.
So next to that, we just have a description of our testing and variable controls. which we don't really want to cover right now since we don't really have too much time. Um, we have just our mission statement here that was given to us, and our mission constraints that Lucy gives us for the mission. Um, just some dates, plans, and milestones. But what we want to go into is the CAD model of Hydril. So with the CAD model, we wanted to keep it simple. Uh, you know, when we were designing the CAD model, we were thinking maybe we can do like a hexagonal type of payload. We just wanted to keep it simple as a circle, just so there's no edges, so it won't get blown over with the wind and dust devils on Mars. So we have it within the constraints of our 50 by 50 by 50 cubic centimeters constraints. And then we have just some very basic drawings of and CAD models of just where we would want to position each instrument. So um, so in the blue, we kind of have our reams. Right here, we have our, in orange, we have our spectrometer. We have our radar down here. And in green, we have our drill hub, which will house our drill. Uh, and then we just have some bottom views of just the CAD model. It won't be clear. We just had to make it clear so you guys can see the different types of instruments that are inside and all that. And then we go into more detail about these systems and all that. Then we'll go into a little bit more about the CAD model. This is just all of our different views and an assembly of the CAD model, and just how big everything is in all of our detail views. And then the rest is just all about integration and how we're going to test our payload, and then what kind of safety precautions we're going to need all the way to the end, which would be our conclusion. So we'll go to our conclusion. So progress on the mission formulation design up to the CDR. Overall, Hydril's mission formulation is near complete. Specifications on more of the structure of the payload and computer hardware will be needed for this mission. A reentry will be needed through the help of companies that have previous experience on Mars applications like Lockheed Martin and NASA. And NASA will be an integral role to the success of this mission, while a different team will collaborate with another to construct the Mars Hydro payload. The design of Hydro will need the ability to be heavier. Adding more weight will allow better results in our ground penetrating radar, since the bigger the radar is, the farther it can scan into the ground. Drills will need to be redesigned to ensure the capabilities of breaking down rocks and soil to excavate the ground and acquire a sample. Further time will be needed to ensure that variables that halt Hydril's mission will need to be looked into to guarantee its success. And we have our references, and that will conclude the video for Team 49's Hydro payload. And we just want to say thank you guys for allowing us this opportunity to be a part of the L Space Academy Level 1. And we will hope to be applying for Level 2 soon, and maybe get our internships done over the summer. And this is Colson Nagiri and Clifford Alvarez signing off. Take it easy, guys. How do we change